Hello everyone, welcome back to Networks class. Last time we did a couple of things. So first we talked about describing graphs mathematically. So you should know about things like what are the predecessors and successors of a node, about sets and multisets, multigraphs, things like that. And then we concluded class by talking about storing graphs in a computer. So we talked about things like the adjacency matrix of a graph, and we just started talking about sparse matrix formats. So the plan for today is to continue talking about sparse matrix formats and just finish up with a couple of different formats that we didn't see last time, and then finish up class by just starting to give you some definitions about graph structure overall. And these definitions will sort of take us into being able to solve our first few network problems. So let's just review a little bit about where we were last time. So last time we talked about the adjacency matrix, and it turned out to be a matrix with a lot of zeros. And it turned out that that took up too much space, so we wanted to figure out a way of storing these matrices with lots of zeros in such a way so that we don't have to store the zeros. And so at that point, we talked about just one sparse matrix format, which is the dictionary of keys format, where we just store the location of the non-zero entries and their values. So for example, the location of this 11 is row 0 and column 1, so that's where we get this 0, 1, and the associated value there is 11. So let's talk about a couple of other ways of storing sparse matrices. So the next way that we'll discuss is called row-based linked list format. And we'll often abbreviate this RBLL. So the idea behind this format is to just kind of think about squishing the rows. So squish the zeros in the rows away. So let's see how this might work. So consider this example matrix that we have at the top here. So that example matrix has 4 rows in it, so rows 0, 1, 2, and 3. And let's think about what's going to happen when we squish things. So think about squishing row 0. The only thing that's going to get left when we squish all the zeros away is just this 11. But we have to remember what column that 11 went in so that we can reconstruct the matrix. So that's what this columns list is going to help us. So there we're going to store just a 1 that tells us where the 11 went. So the idea here is that we're going to store these two lists for every row. So a data list that tells us what the actual values are, and a columns list that tells us what columns those values go in. So if we look at row 1, the data list for that is going to be a 12 and a 13 because those are the two non-zero entries. And the corresponding column list is going to be a 0 and a 2. So similarly for row 2, the data list is going to be a 14 and the column list there is going to be a 3 because this 14 is just in the third column of the matrix. And the last row, row 3, has no non-zero entries, so both of these lists are just empty lists. So given this information right here, that's sufficient to reconstruct the entire matrix at the top of the page. So let's ask the same 3 questions that we were asking last time of this particular data structure format. So first of all is how much memory does this format take? And to answer that, let's keep the following couple of definitions in mind. So n is going to be the number of rows in the matrix. And m is going to be the number of non-zero entries. So when we introduced n and m earlier, I said that n is the number of vertices in the graph and m is the number of edges in the graph. But really that directly maps to this because every edge creates a non-zero entry in the adjacency matrix. And that's why the number of edges and the number of non-zero entries is exactly the same. Similarly, in the adjacency matrix has as many rows as there are vertices in the graph, which is why the number of rows we're saying is n. So in terms of memory here, and in terms of big O notation, the number of lists that I have to have, regardless if the list is empty or has some material, is n. So I know that for a fact I have to have n items. It's going to be at least n empty lists. And then in addition to that, these lists in total are going to have m entries in them, which is the total number of non-zeros in the entire matrix. So this is the total number of entries. And this is the number of lists overall. So memory is O of n plus m. And what about accessing? So if somebody comes along and says, is edge 1, 3 in the graph? How quickly can we answer this question? Well, to answer for 1, 3, what you have to do is go down to the appropriate row number. So if they're asking us about 1, 3, we would go to row 1, and we look at this column list, and we'd have to look through this entire list to see if 3 is somewhere in that list to know if 3 is a successor to node 1. So the amount of work that we have to do is basically equal to the length of this list. Now the length of this list is simply the degree of whatever the node is here. And so we can just answer this access time conservatively by saying it's big O of the maximum degree in the graph. That's because the maximum degree is exactly how long these lists could possibly be. And to find if AB is in there, I have to look through that list. So the third question that we were asking is how long does the successors operation take? So if somebody comes along and asks us for the successors of node 1, what we can do is just go to row number 1 and immediately return this list right here, the list 0, 2, because those are exactly the successors of row 1. So answering the successors question takes us very little time, just O of 1 time. And this is great because that's the one operation that we wanted to get to be really fast. So successors works really well here. Access is pretty good. You know, this is not bad. And memory is also very good because you can't really do better than O of m memory. So that's the row-based linked list format. So let's discuss our next format. So the next format is called compressed sparse row format. So compressed sparse row. And we'll often abbreviate this as CSR. So in some sense, compressed sparse row format is the most complicated format that we'll learn, but it's also the most widely used format. So for example, if you go into Cplex and you try to specify a linear program, Cplex will expect you to give it the linear program, the constraint matrix A, in this kind of compressed sparse row format. So the way to get this is always start with the RBLL format. So that's the format over here. And the basic idea is that all of these lists that we have, we want to turn those into arrays because array access is fast and accessing lists is very slow. So the idea is we're going to take this columns list and we're just going to turn it into an array. So here it is. We have columns. We're going to have data. And we're just going to take what we had in RBLL format and turn it into an array. So we're just going to have the array have the following entries: 1, 0, 2, and then 3. So 1, 0, 2, and then 3. So I got that by just going through and writing down all of the entries in RBLL here. And so similar thing for the data, we can just go through and write down all of these. So it'll be 11, 12, 13, and 14. So 11, 12, 13, and 14. But the problem is now that when I did this, I don't know where each row starts and stops. So I've lost the starts and the stops here. And that's why we're going to have a third piece of data here, which we're going to call index pointer. And the idea behind index pointer is it's going to tell us the starts and stops. So let's talk about how to just mechanically get index pointer. So mechanically, you do it like this. You always start index pointer with 0. So here it is. I started it with 0. And then what we're going to do is you're going to add the length of the next list to the previous number to get the next number. So this might be slightly confusing just written down in English, but let's just do this example and I think it'll become clear. So to this 0, we have to add some number to get the next number. And the number that we're going to add is that we're just going to process these rows one at a time. So we're processing row 0. So we have to add the length of the columns list here, which is 1. We have to add that length to the 0 to get a 1. For the next number, we have to add the length 2 to 1. And so the next number we're going to get is 3. To that 3, we have to add a 1, which is the length of this list right here, to get a 4. And then to that 4, we have to process the last row here. To that 4, we have to add a 0 to get the final number, which is going to be a 4. So that's how we mechanically create index pointer. But let's see what it means. So we got these two numbers, the 0 and the 1, by looking at row 0 of the matrix, right? So the length of row 0's list was 1, and that's what gave us the difference between these two numbers. And that actually directly maps to the starts and stops over in the columns array. So this 0 tells us that row 0 starts at the beginning, and it consumes exactly one of those entries. And it consumes one of those entries because the difference between 0 and 1 is 1. So that's how I know it consumes one entry. So for the next row, for row 1, I know that it starts at 1 and then consumes 2 entries because the difference between 1 and 3 is 2. So those are the values that row 1 consumes. Then row 2 starts where row 1 left off, and it's going to consume 1 entry because the difference between 3 and 4 is 1. And then row 3 starts at the end here and consumes nothing because the difference between 4 and 4 is 0. So at this point, this information is enough to reconstruct the whole matrix because I know exactly the row numbers, the columns, and the data values for each of the pieces of information to create the matrix. So that's the basic idea of compressed sparse row format. But let's just discuss a couple of other details. So first, the length of the data array. So all three of these things are array. So index pointer is an array, columns is an array, and data is an array. So the length of the data array here is going to be m. So that's the number of non-zeros in the matrix. And that's because we have to store all the non-zero values. So that's why there's going to be one entry here for each of the non-zeros. So similarly for the columns here, this is going to have length m. Again, because I just need to have one entry for each of the non-zero values. But what about this guy? What about index pointer? Well, index pointer doesn't have to do with the number of non-zeros. Its length has to do with the number of rows in the matrix, because every row corresponds to a little gap between two numbers in index pointer. So the length of index pointer is going to be n plus 1. And that's because every row is going to land between two of the numbers right there. And so the point is that these two things are not equal to each other. So you might have index pointer be longer and columns be shorter, or maybe columns be very long and index pointer be short. So the two lengths do not have to be the same at all. So let's just practice one more time, creating a matrix into compressed sparse row format, just to make sure that we understand how it works. So let's take a new example here. So here's a matrix. Let's say the rows are 0, 1, 2, 3, and 4. 0, 1, 2, and 3. So this works for any matrix. It doesn't have to be square. So here I've created a non-square matrix. And so let's put down some entries. So let's say the first row is all zeros. The next row 11, 12, 13, 0, 0, 0, 0, 0, 0, 14, 15, 0, and then let's say 16, 0, 0, 0. Okay, so that's my sparse matrix with lots of zeros in it, and I want to turn it into compressed sparse row. So the first thing I need to do is make it into a row-based linked list. So that's going to have a row number, a columns list, and a data list. So the row numbers are 0, 1, 2, 3, and 4. And so let's do the columns list for row 0. Well, row 0 has no non-zero entries, so the column list is empty. And similarly, the data list is empty because, again, there's no non-zero entries. So let's do row 1. So row 1's columns list is going to be 0, 1, and 2, because those are the columns that have non-zero entries, and the data list is going to be 11, 12, and 13. For row 2, it's going to be a couple of empties again, it looks like, because no entries in there. For row 3, it's going to be 1 and 2 is going to be the columns list, and the data is going to be 14 and 15. And for 4, the columns list is just going to be 0, and the data is just going to be 16. So we took this matrix and we turned it into RBLL, but now we have to turn it into compressed sparse row. So let's do that. So I need a columns array, a data array, and an index pointer. So the columns and data arrays are probably the easiest to get down. So we get those by just going down here and writing these numbers down. So columns is just going to be 0, 1, 2, 1, 2, 0. Data is just going to be 11, 12, 13, 14, 15, 16. And then let's construct index pointer. So to construct index pointer, we always start with 0. And then to this 0, I have to add the length of the first list, which is 0 here. So I'm going to have another 0. Then I have to add the length of the next list, which is 3. So that's why the next number is going to be 3. Then I have to add 0 to that, so I get another 0. Then I have to add 2 to that, so I get a 5. So that came out of adding the length of this list to that 3. And then to that, I have to add a 1. Which is the length of the final list. So let's double check to see if we did this correctly. So here, our number of rows was 5. So that means I should have 6 entries in index pointer, because the length it was n plus 1. So yep, indeed I have 6 entries in index pointer. But there's actually another way to check, which is this last number here, the very last number in index pointer. This should always be equal to m. And that's because at the end, all the entries in the columns array have to be consumed. So this last number here has to be equal to the number of non-zeros that we had in the matrix. So in this matrix, the number of non-zeros that we had was equal to 6, right? Because there's 3 non-zeros here, 2 there, and 1 there, so 6 total. And that's indeed the last number that we got for index pointer, so everything looks pretty well. So we took this matrix and we turned it into compressed sparse row. And if we had to do it the other way around, if somebody gave us this compressed sparse row and asked us to reconstruct the matrix, we can do that just as easily because we know that row 0 starts at 0 and consumes 0. Row 1 starts where row 0 left off and consumes 3. Row 2 starts where row 1 left off and consumes 0 in this particular case because 3 minus 3 is 0. The next row starts where the previous one left off and consumes 2. And this one starts out with the previous one left off and consumes 1. And so I know this was row 0, row 1, row 2, row 3, and row 4. And so that's exactly all the information that we need to construct back this original matrix. So very good. By now, we should all understand how to take a matrix and turn it into compressed sparse row format. But let's ask our 3 questions that we've been asking of all these data structures, which is, first of all, how much memory does this take? And the answer here is O of n plus m. And probably the easiest way to see that is by just taking a look at these lengths that we had up here. So the length of index pointer was n, and the other 2 lengths were m each. So that means in total, I must be consuming O of n plus m space. So what about access? So somebody comes along and says, is edge AB in the graph? Is edge 1, 3 in the graph? And to answer this, what we have to do, if they're asking us for 1, 3, is I have to go look at row 1 and figure out what part of the columns array that corresponds to. So that would correspond to these 2 entries in particular. But now these 2 entries are in an array and not in a linked list. And in particular, we could make sure that this array is sorted. So we can make sure that each of these little segments in here is sorted, and so we can do our binary search trick on that array. So if we do that, then the running time for access would be just log of the max degree. And the log here comes from doing that binary search trick, and the max degree comes from the fact that that's the biggest that each of these segments could be, is just the maximum degree. And again, that's just because one of these lists, the longest it could be, is just the maximum out degree of a node. So what about successors? How fast can I find the successors of a node? Well, if somebody comes along and says, what are all the successors of node 1? All I have to do is return to them this segment of the array. And I can find that out very quickly because I can just jump to where row 1 is. This immediately tells me where that row starts. The difference here tells me where that list ends, and so I know immediately what the successors are. So that's O of 1 time, very fast. And this is probably another reason that this is one of the most used data structures, because successors was a great running time, access was pretty great, and memory was pretty great. But another reason is just because how simple this data structure is. All it takes is just 3 arrays, and so you can use it to kind of communicate across different computer programming languages, etc. And that's one of the reasons that so many computer programming libraries use this data structure to specify sparse matrices. So that pretty much concludes our discussion of sparse matrices, except I want to bring up a couple of more points. So the first point is that there's just nothing special about the rows. So we've been talking about row-based linked list and compressed sparse row format, but just as easily as sort of squishing down all of the zeros out of the rows, we could have squished down all of the zeros out of the columns. So let's just, for practice, write down something that we'll call column-based linked list. Or let's abbreviate this CBLL. So to do column-based linked list, what we need is a column number, a rows list, and a data list. So we'll just use this matrix that we had over here as an example. So I had columns 0, 1, 2, and 3. So we can go and enter these 0, 1, 2, and 3. And now let's figure out what the rows list for column 0 is. So column 0, the row list is 1 and 4. So I won't do the data because that's straightforward. So what about the rows list for column 1? It's going to be 1 and 3. And the rows list for column 2 is going to be 1 and 3. And the rows list for column 3 is just going to be empty because there are no non-zero entries in the third column. So this is empty. And these data lists are whatever they are. So partly I bring this up to get some practice with these column-based formats, but I also bring it up for another reason, which is, let me ask the following question. So we've been asking about successors. So how fast is it to find the successors of a particular node here? So let's say that somebody came along and asked me to find the successors of node 3 in this graph. Well, to do this, you actually have to go through each one of these lists and look for every list where 3 appears. So I would look through this list and say, oh, 3 doesn't appear. That means that 0 must not be a successor of 3. Look through this list and see, oh, 3 does appear, which means 1 must be a successor of 3. Oh, 3 appears in this one, which means 2 must be a successor of 3, and so forth. So successors actually takes O of n plus m time. And that's because there's n lists for us to look through and m entries to look at in total over all of the lists. So successors is actually very expensive, but what about predecessors? So if somebody comes along and says, give me all the predecessors of node 1, well, they're right here. They're already stored in this linked list. So predecessors turns out to be really fast, just O of 1 time. So the point I want to make here is that there's just this asymmetry between the column-based formats and the row-based formats. So in the row-based format, successors was really fast, but as you might imagine, predecessors here for compressed sparse row, or RBLL, predecessors is quite expensive. So it's O of n plus m time to do predecessors in RBLL. So we can get one of these operations to be fast, but it makes the other one be slow. So just out of curiosity, if you did happen to want both predecessors and successors to be fast, then what you could do is, if you're willing to pay twice the memory, is just store the graph in 2 different ways. Store it both in compressed sparse row and compressed sparse column. So if you have both of these, then depending on which question you get asked, you just use the right one to answer the question. And so by doing that, you could get a total runtime of O of 1 for both successors and predecessors. But of course, what you would be paying is just twice the memory expenditure. So these compressed sparse matrix formats are just very, very common across multiple topics. And so it's worth it to think about them both from the point of view of networks, as we'll use them in this class, but also in terms of just sparse matrices overall. So that concludes our discussion of storing graphs in a computer. But let's quickly sort of take a look at our next topic, which is some definitions on graph structure. And the first definition that we'll look at is the definition about paths. So we say that a simple path is a sequence of nodes let's say A1 up to AK, where no node repeats and every edge AI plus 1 is in the graph for I equals 1 up to k minus 1. And we say that non-simple paths allow repetition. So the reason that I put the word simple in parentheses at the top here is because oftentimes you'll hear people just say a path. And usually when they say a path, they really mean a simple path. And the reason that people make the distinction between a path and a simple path is the following. So suppose that I'm going from a node A to a node B, and somebody gives me some non-simple path. So in other words, I'm going from A to B, but some node in that path repeats. Let's say node C repeats. Well, if that's the case, then I can go from A to B in a much more direct way by just cutting out this loop. And so that's why simple paths are typically the kind of thing that we're interested in, and we're typically not so interested in non-simple paths. But let's just take a look at some examples to make sure that we understand this definition. So here's a couple of example graphs. So graph 1 looks like this. And let's see what we can say about paths here. So let's take a look at this sequence of nodes 0, 1, 2 and ask ourselves, is that a path? Well, what we have to do is we have to just check if every sort of pair here is in the graph. So 0, 1, that's an edge, so that's good. And 1, 2, that's an edge, so that's good. And so this is a simple path because no node repeats and all of the appropriate edges are in there. So what about this next example? Let's take a look at 0, 1, 2, 0, 3. If you take a look at this, this is a non-simple path. So why is that? Well, certainly we know that it can't be simple because node 0 repeats, but let's see if it's a path. So 0, 1, that's an edge. 1, 2, that's an edge. 2, 0, that's an edge. And 0, 3, yep, that's an edge. So that's a non-simple path. But what about 0, 1, 2, 0, 4? So if we look at this guy, first of all, we know he's non-simple because he repeats some node. 0, 1 is an edge. 1, 2 is an edge. 2, 0 is an edge. But 0, 4 is not. So 0, 4 is not an edge, which means that this is not a path. And so this definition is actually quite intuitive. I mean, it's just telling you, can you start at the first node and keep walking along this sequence of nodes, following all of the edges. And so this is an example with a directed graph, but let's just do one quick example with an undirected graph. So here's an undirected graph, 0, 1, 2, 3, and 4. So what about the sequence 0, 1, 2? Is that a path? Well, 0, 1 is an edge and 1, 2 is an edge, so yes, this is a simple path. And what about 2, 1, 0? 2, 1, 0? Well, that's also a simple path. And the point is that in an undirected graph, we could take the edge either from 2 to 1 or from 1 to 2. It doesn't matter. Whereas before in this example, it really did matter in which direction you were taking the edge. So that's our first definition about graph structure. And let's take a look at one more definition. So we say that a cycle is a path A1 to AK with edge AK A1 also in the graph. So I want to highlight that when I say a path here, I really mean a simple path. So let's see what this definition means by looking at some examples. So let's just look at this first graph that we drew at the top, and look at this sequence 0, 1, 2. And let's ask the question, is that a cycle? So 0, 1, 2, first of all, that's a path. I know that. And then the other thing that I have to look at is to see if there's an edge from the last node of the path back to the first one. So 0, 1, 2. So is this edge from 2 to 0 in here? Yes, it is. So yep, that's a cycle. So let's take a look at another example. What about 0, 1, 2, 0, 3, 4? Again, in this first graph. Well, 0, 1, 2, 0, 3, 4, that's a path, or that's a non-simple path because it repeats node 0. And then 4, 0 is in here. So this is not a cycle because it's not a simple path. And so what happened here is that we really saw two cycles that are just put next to each other. So one cycle was this 0, 1, 2 cycle, and another cycle was this 0, 3, 4 cycle. But together, they're not a cycle because they're not simple. So let's take a look at one example from number 2. So what about 2, 3, 0, 1? Is that sequence a cycle? So 2, 3, 0, 1. That sure is a path, and the edge 1, 2 is also in the graph. And so, yes, this is a cycle in the second example over there. So, so that's the two basic graph definitions that we need to define the next problem that we're going to study. So we're not going to get to actually solving this problem today, but let's just define it. So we're going to look at the shortest path problem. And this is just a very intuitive problem. It's the kind of problem that you would try to solve if you're trying to create some kind of routing application, for example. So the idea here is that we're given a graph with some edge lengths. So let's say that Cij is the length of edge ij. And let's say that we're also given two nodes, S and T. So these are our special nodes that are going to determine the start and end of our path. And our goal is to find the shortest, by which we mean minimum distance, path starting at S and ending at T. And so this is kind of a very, very natural problem to think about in terms of networks. But let's see when this problem makes sense and when it doesn't. So intuitively, when I define this problem, you might naturally be thinking that these Cij's, since they're lengths, they should all be positives. But it turns out that the Cij's might be negative. So we might want to do some kind of modeling where we create a graph with some negative edge length. So just to give you an example about that, um, you can think of trying to trade in foreign currency exchange. So the nodes here would be the different currencies, and taking an edge from one node to another means that we're performing the corresponding trade. And depending on whether we lost money or gained money on that trade, you can think of that as a positive or negative edge length on that edge. And so the idea here is that if we could find some kind of cycle in this graph that ends up making us money, then we can do those sequence of trades to kind of make money on the foreign currency exchange. So there are some modeling applications where we want the CIJs to be negative. But let's see when shortest path makes sense and when it doesn't. So imagine that this is the graph here. And so this is node S and this is node T. So we start at S and we want to get to T. But let's say that in the middle of this graph here, there's some kind of cycle whose total length is negative. So if that is the case, then when somebody asks us for the minimum distance path from S to T, one of the things we could do is just start at S, go to this cycle, and just spin around this cycle many times over, just spinning around here. And for every spin, we would add to our length some negative number. And so if I spin an infinite number of times, I could get the total distance to be minus infinity, and then I could get to T. So the point is, if there's this negative length cycle, then the shortest path problem is really not that well defined. So to really define this problem above, we'll assume that there are no cycles whose total length is negative. So what I mean by this, just to give you an example, is just something like this. So here's a cycle. Maybe this length is 10. Maybe this one's minus 30, and this one's 2. So that the total length as we walk around here is negative. And so if I keep spinning on here, I'm just going to be getting more and more negative of a distance. So we're going to assume that there's no cycles whose total length is negative. And then next time, we'll see how, under this assumption, we'll be able to solve the shortest path problem using a linear program. So thanks a lot for listening to the lecture today, and I'll see you all tomorrow.